Students, welcome back to the second part of the lecture number 5. So, we have been talking about issues related to multivariate functions, and this is what the last slide I discussed with you, how to calculate Hessian, and then Hessian can be used to find out the optimum points or saddle points. But you have to also look into aspects of convex and non-convex functions. By the way, most of these error function or loss functions in deep learning are non-convex functions. So, you have a convex function, then you also already have a Goel minimum. You can see that is your optimum function, right here. What about non-convex functions? You have local minimas. You can see there is a local minima here. So, there are many local minima here, loss functions, many. There may be only one Goel minima here, there are many local minima. So, the problem is that when you devise a computational technique to find out the error, minimization of error, you have to hit the Goel minima. But instead, if you get into a local minima or get trapped by local minima, you will not be able to handle it, right. That is why these non-convex things are very functions. So, convex fx is a convex, what will happen? All the chords will lie above the function, right. You can clearly see that all the chords, but non-convex functions, that is not true. You can clearly see that the chord, all the points of the chords are not above the chords are not above all the points of the curve, right. Here every point of the chord is above this function everywhere on which is plotted, but that is not the case. Some part of the curve is above this chord here for the non-convex functions. That is why the local minima comes into picture. So, therefore, first order convexity, that means graph of f must be above all the tangents, that is what it is. Second order derivative of Hessian must be positive, also semi-definite. Okay. So, that is why the Jensen's inequality comes into picture. The concept is chord lies above the functions. That normally means if f is a convex, then these are the variables alpha 1 to alpha n, or the functions. If you add it up together, it becomes 1, and if you do f of alpha 1 x 1, sum it over, that must be less than this alpha into f x. Okay. These are actually Jensen's inequality, that may be valid for the convex functions. You can check that. But remember, when you know it is a convex functions, you can easily handle this issue of finding Goel minima. That is why you do this. We test the convex function is there or not simply by using Jensen inequality. That is why the aspects of gradient descent come into picture. Okay. It is widely used for ridge regression and linear regression, you know that, the first order optimality. I will not go back into region and these regressions, this is widely used as a regularizer in regression analysis. So, first order optimality what? Gradient g must be equal to 0 at the optimum value or minima or maxima, whatever minimum is considered. So, therefore, we make this 0 and solve w's, that is what we have been talking about all throughout. I am only showing you how it is to be done, and this closed form is available, then we are done, solve the problem. If closed form is not available, then you have to use what is known as iterative technique called a gradient descent, right. That is what we discussed in the last lecture. So, this is what is your gradient. You can see that this is your loss functions with a gradient, put it 0, you get a closed form solutions, answer is done. If you do not get a closed form solution, then only gradient descent issue comes into picture. So, it must we must tell what is gradient descent learning algorithm is. The purpose of this algorithm is to define the error functions that measures how good the predictions are. That the partial derivative you can see here, that is what I told you in the board also, and then we add learning rate, and that determines the step size by which you will move. I will explain you very clearly how it can be done. The learning rate is nothing but a step size by which you are varying the x variables, okay, and check these error functions, and then we keep stepping through this weight space until you reach the Goel minimum. Okay. So, that is what I discussed with you for derivatives of sigmoid functions. Takes particularly simple form because that is the property of the sigmoid functions. Okay, that is in a nutshell what is it. So, if I have to explain to you nicely, I have shown you this slide which is taken from Greeks.org. This is basically akin to find the lowest point of a hilly area by walking down the slope step by step. So, you are going down this thing, going up, going down till you reach this point, saddle point or global point. Okay. So, you can see every time you move, which direction you will move? You are moving this direction. How? Because you are calculating the gradient, and gradient is slowly going down, right, here. So, once you reach here, then you see gradient was negative, that is fine, I reached, but the moment I go up, gradient become positive, right. That means I am doing the wrong direction, I should again come back. So, to explain you further, gradient of a function is nothing but a slope, right. Slope is depends on the direction in which it is measured. You should do the vector calculus or look at books of vector calculus. You can find out how to calculate gradient in a particular direction or vector. Okay. So, hence gradient provides the vital information about the rate of change of the function's output with respect to the inputs. Why, how y is changing, or rate of y is basically depends on change of x, that is what it tells you, right. So, step 1, what you do? You begin with top of the hill, that means you start with any random guess, and then you step 2, you feel the slope, look around, find out whichever is the steepest slope. Like if you go back here, you find this is the steepest slope, right, this direction. So, you should go down that way, that is what it is, if you want to reach the minimum point very fast. And that is what it tells you, gradient tells you the steepest way downfall. In step 3, move in the direction where the slope is steepest, that means you adjust your model parameters or the W's basically, bigger the slope, bigger the step you can take, but there is a danger here. If you take a bigger slope, you may not hit the global minima, you may go out also, we will talk about it. And then step 4, you repeat that. So, this will be done and again iterative process till you minimize the error. Okay? That is what the idea is. And fundamentally, this basically done by simply adjusting the model parameters, reduce the weights difference between the predicted actual values. To give an idea, let us say this is my cost function as a function of weights, and this is what is. So, therefore, you take initial point, calculate the gradient here, gradient is slope, you can see that slope, and then move this direction. So, keep on calculating the gradient every step till you reach this the minimum point, right. That is what it do. So, now let me come back to this. So, what is the learning rate? Okay. So, basically it tells you that step at which you are varying these points. So, let me take you through, this is the loss function versus weights. Okay. So, you can write L is a better loss, and you see here we are moving very small. That means what? If I start from this point, I go to the next point here, this is what is your difference delta x, that is what is your learning rate, right. Again you go from here to there, another delta x, another delta x, another one. So, this is less than the optimum. Now, you can also take a very long delta x from here to here, this is very large x delta x, correct. That is not a good. If you take a little higher, you will hit here instead of hitting here, that is not the global minimum. Or you can basically take a value between optimum and twice of the optimum, that is what you see, you have taken a value like that, reached here. So, reduce it. So, the moment gradient become positive, this was the gradient was negative, you taken the slope, it has become positive, okay, going up. So, you have taken this direction, again this direction, again this direction, finally reaching that. Okay. And if you take a very large learning rate, that means very large step, then this is what will going to happen. This is taken from the book of Richard O. Duda, Peter E. Hart and David G. Stock, Pattern Classification, John Wiley and Sons. Okay. And gradient descent works very nicely when functions are differentiable. That means if function is not differentiable, you cannot calculate the gradient, so you cannot use it. And also it should have a convexity. the cost function should be ideally convex. I talked about it, but that ideality never, most of the cases, does not happen in deep learning. So, the convexity is lost, then you have a non-convex functions, that is why the problem comes. I discussed about it. Okay. So, now let me talk about more about that. So, in gradient descent you simply initialize w's as a w0, iterations start from 0, 1, 2, 3, calculate the gradients t, set the learning rate as I discussed now, and move in the opposite direction of the gradient. Okay. So, for convex function, gradient descent will converge always to global minima. Good initialization is needed for non-convex functions, very important. So, learning rate is very important, it should be set up optimally. So, let me just explain to you this plot. This is a very interesting plot. This is a loss function as a function of w, right. This is what it is. Now, what is that? Let us say start with a initial guess is this is a w 0, right. Take a slope here, you can see that slope. So, now this slope is negative. So, you can move in the positive direction. This is what is your learning rate, you can see that delta w. So, you moved it, correct. Here you go back again. Let me show, this is what you calculate the slope, this point here, that is less than 0. So, you can move in this direction. It has to be reducing, right, slope has to be reducing all this. Now, this is what is your step size or learning rate. Okay. So, you come here, again calculate the slope, and you see slope is what? Negative. You move again further, that is your next step. But you, since you have taken a step size more than the optimum size, you cross the global minima and reach the other side. Okay. You can see that. Take the slope here, you see slope is become positive. So, that means we are moving in the wrong direction. So, again you move back and finally you reach the optimum values or the global minimum. So, you understood that, right? I can play it again for your purpose. So, start with a starting point w0, calculate the slope or gradient, and you see this is the gradient here, gradient is negative. So, you can move in the direction in which the curve is. So, take a step, that is delta w, and move here, correct, you can see that. So, we moved here, again calculate the slope, slope is still negative. So, you can move in the right direction. We go to the next step, we reached here, again calculate the slope, slope is positive now. So, you have to move in the negative direction, that means backward, so that you reach the global minima. This is an iterative process, you understand, right, very clearly. This is an important iterative process by which you can reach the local global minima of the error or loss functions. Okay. So, there is on the other side there is another one, local minima. You can do that, right. You can see I moved from this step to this step, again calculate the slope, but we crossed it over. If you calculate slope, it becomes positive, you have to go back to reach the local minima. Okay. But this is a local minima, this is a global minima, you have to always reach the global minima. Very simple example of the effect of learning rate, I talked about it, again I am giving you. If you say very large learning rates, this is what will happen, you will never reach this local global minima, you reach somewhere else. Okay. Very large learning rate by very large step size. I hope you understand now the learning rate is nothing but a step size. So, if you keep on doing that, so you are reaching here somewhere there. So, let us take another example of gradient descent, where we will explain about the effect of learning rate. As you see here, the learning rate is very large, very large rate actually, So, initially it was going like this, then from there it goes like that, then it goes like this, then here. That is what, then you reach, you may not reach your global minima here, and if it is a very large rate, it will reach even here, the region near to the local minimum. So, if it is a very small learning rate, what will happen? It will take a too long time to converge. You can see you have a very small step, like a baby step, right. It will take too long time to reach. Sometime may not be able to cross the global one, it may stuck here at the things. So, that is what is the optimum level of learning rates to be used. Okay. So, you know, in case of gradient descents, so what do you do? Weights are optimized by this way. I told you in the last lecture also. So, this is the new weight. This is your old weight. Okay. This is your learning rate. Or step size, and this is your gradient. So, that is how we can optimize the weights. So, initialized, so this is your step of setting new weight. So, obviously, in step 1, you just initialize weights as a W0, correct. Steps 2, you calculate gradient, GT, that is your gradient, and then step 3, set optimum learning rate, not very large, not very small, step size basically. You can find out this from your, you can find out that from your loss function versus W plot. Okay, if it is very slopey, slope is very steep, you have to use small learning rate. If slope is, slope is not very steep or rather shallow, you can use high learning rate. Am I clear? So, learning rate is very, very important. And the step 4 is that, this is step 4, setting the weights, correct. And the moment G, T become positive, you have to move opposite direction. I explain you, if you have not understood, you can do yourself. You go this way, moment you reach here, your slope is increasing, so you have to go back. Initially you are going this way, okay, you reach here, from there you reach here, then you see it is going up, slope is positive. So, you have to move backward, that is what is called opposite direction. This is the basics of gradient descent technique. So, there are many other gradient descent techniques which are useful. We will talk little bit about some of these. So, one is called as stochastic gradient descent, or what is called as say SGD, correct. So, it is basically in SGD, it updates the model parameters, basically your weights after each training example, making it more efficient for the large data sets. In traditional gradient descents, it uses entire data sets for updates, but in stochastic one, you use only certain sets. Let us say training example, particular training example, not all the training data, and then compute the gradient of the loss functions, update that. That is what happens. Okay. So, this is what is shown here. You can see that very nicely. The gradient here is moving. So, you can see this is the stepwise. So, you have a local minima here, this is a global minima there. So, it's we do not select all the training example, we do not start from beginning to end. We select any specific training example here, calculate the gradient, move here, move down, go to local minimum. Okay. So, that way you can actually calculate how things are varying locally. That means using a very simple small training data sets. That is why it becomes a very efficient technique. You can also use mini batch gradient descent, which is also very useful tool, mini batch gradient descents, correct. And okay. So, yeah, here it is a predetermined number of training example, and which more smaller than the full data sets, predetermined number of trainings, remember that. That is what it become mini batch. You can see that every step one batch, like this one or this one batch, correct. That is what is done. So, this way you can improve the efficiency of the gradient descent techniques. And last one is called a SGD, or gradient descent technique, okay, with momentum. Remember SGD, right, stochastic gradient descent, you can use with momentum. By using momentum, we can accelerate the convergence, basically by smoothing out the noisy gradients of the SGD. That is the idea. So, what is the idea? So, as you know, in stochastic gradient descent, we are using a certain training examples, but here you are using moments. Okay. So, if you have to put in a mathematically, then you can write down certain equations in a gradient descent. Okay. So, let me just tell you that this is important, that is what I tell you. So, this is called a SGD, stochastic gradient descent with momentum. So, what is that equation you use? What is the way we have to update the weights? So, W t plus 1, this is standard one, is become beta into W t one plus, then 1 minus, this is not a beta, this will be eta t, learning rate, 1 minus eta t multiplied by gradient of the function, loss function, some step theta t. Okay. So, this is what is the new thing here. So, you selecting a particular learning rate, and to optimize this weights, you can see here, but we were not using the gradient here, we are using the gradient there. So, basically we should write down this is as a GT. Am I clear? That is the idea. This is the main concepts. So, these are very advanced optimizers, where it is not a WT, this will be VT, and this VT is momentum. Sorry about it. VT is the momentum. Okay. So, that momentum means you are adding extra term there. The momentum allows you to calculate the model parameters. Okay. That is the main idea. So, here you can see in the plot, you can clearly see that in the plot, this is loss function versus W, and we are changing the W, this is step 1. So, each step we are increasing the step size, that is what is the momentum is doing, that. Okay. Each step you are increasing this, so that means you are increasing your learning rate by a factor Vt. Okay. That is what is done, and then you calculate the change. So, that way you can actually quickly converge, but remember this requires you to have a smooth convex function, which may not be case always. So, these are the three different types of variations of the gradient descent techniques. So, let me just also tell you there are many others. There are many advanced optimizers like ADAGAD, RMS prop or adaptive momentum estimations. So, you can read it through. I am not discussing all these aspects. I discussed the basic principle. You can always build on this, right. So, the next lecture we are going to talk about convolution neural network. Okay. So, that is what we are going to start, and the important aspect in convolutional neural network is to how to analyze images, right, very important. So, we will start with how computers use images, and then we can discuss how we can understand that. That is the main aspect of convolution neural network, which will be discussed next 4 lectures. So, please keep your concentration on, so that you can understand it very well. So, with this let me stop the lecture number 5. Thank you.